Rare earth element separation introduction. Rare earth elements: 17 metallic elements, 15 lanthanides. Those are neodymium, cerium, terbium, praseodymium, lanthanum, dysprosium, europium, samarium, gadolinium, holmium, lutetium, thulium, ytterbium, erbium, promethium, plus yttrium and scandium. Lanthanides are highly dense metals with high melting points. They form alloys with other metals. These are F-block elements that are also referred to as the inner transition metals. 4F series, lanthanides. 5F series, actinides. 4F characteristics: have a luster and are silvery in appearance. Soft metals that can be cut with a knife. The elements have different reaction tendencies depending on basicity. Some are very reactive, while some take time to react. Can corrode or become brittle if they are contaminated with other metals or nonmetals. They all form mostly a trivalent compound. Sometimes they can also form a divalent or tetravalent compound. They are magnetic. The ionic radii of tripositive lanthanide ions decrease steadily from lanthanum to lutetium due to increasing nuclear charge and electrons entering inner f orbital. This gradual decrease in size with increasing atomic number is called lanthanide contraction. As the size of lanthanide decreases, their basic strength decreases as well. Therefore, lanthanum hydroxide is more basic than lutetium hydroxide, which is the least basic, because of the smaller size but higher nuclear charge. The tendency to form coordination complexes increases from lanthanum 3+ to lutetium 3+. Individual rare earth elements don't occur in mineable concentration in Earth's crust, but are naturally mineralized together and must be chemically separated to use for technological applications. Their physical and chemical similarities make them extremely difficult and costly to separate, while generating a lot of waste. Extraction and separation of rare earth elements for technological application occurs largely overseas. ORNL is working on new extraction agents based on diglycolamide. Acidic extractant, PC88A, operates by pH swing, while DGAs operate by an anion swing and show higher affinity for lanthanides with smaller ionic radii. Liquid-liquid separation is the most accepted technology for recovering individual rare earth elements and can be continuously operated. Extractant transfers metal species between two immiscible phases. The extractants hold metal ions using electron-rich donor groups such as oxygen, sulfur, and nitrogen. Key in rare earth element extraction is the selection of ligands with number and arrangement of functional groups, as well as lipophilicity, size, and viscosity. PC88A is a phosphorus-based extractant, and while it has a good loading capacity, it only has a separation factor of 1.2. ORNL has been experimenting with a DGA called Togda, which has a separation factor of 2.5. However, it has about 1/5 of the loading capacity of PC88A. At concentrations higher than that, gelling or precipitation could be a problem. It is hoped that structural changes to the DGA could improve its loading capacity.